Before venturing further into this course, let us first introduce a fluid and discuss some of its properties. A fluid is a material which cannot resist shear without moving. A solid, on the other hand, resists deformation initially. Once a certain threshold is reached, a solid begins to deform and its deformation is proportional to the applied shear stress. When the applied shear stress is removed, a solid stops to deform further. In contrast, a fluid deforms continuously when a tangential force is exerted on it. The magnitude of this force does not matter. Deformation will start as soon as a force of any magnitude is applied to a fluid, no matter how small or large. Moreover, a fluid continues to deform when the force is removed. It is necessary to mention that the distinction between fluids and solids is not always sharp. As previously mentioned, a collection of granular solids sometimes behaves as a fluid. Remember the video of sand flowing through your fingers? Another example is that of a solid behaving similar to a fluid under extreme pressure. Potassium, when subjected to extreme pressures, can exist both as a solid and a liquid simultaneously. In order to understand the behavior of fluids in certain conditions, we have to first understand the fluid properties that govern its motion. These properties at a point represent an average over a small volume. The dimension of this small volume is large compared to the distance between individual fluid molecules, but is small enough to be represented by a point in space. The assumption stems from the treatment of fluid as a continuous medium and is commonly referred to as fluid continuum. The measure of this assumption is provided by a dimensionless number called Knudsen number. It is defined as the ratio of molecular mean free path to the characteristic length scale of the problem. Molecular mean free path generally refers to the average distance traveled by a fluid molecule between successive collisions. If length scale is much larger than the mean free path, fluid continuum is valid. Knudsen number is large for rarefied gas flows. In these cases, fluid continuum assumption is not valid. The assumption of fluid continuum is the primary basis for deriving the governing equations of fluid motion. The mass of the fluid in a given volume is governed by the number of molecules and the molecular weight of the fluid. The density of the fluid is the ratio of the fluid mass to its volume as volume shrinks to a small number. Gases are less denser than liquids as they move freely and therefore can be easily compressed. Molecules in a liquid, on the other hand, are close to each other and therefore cannot be compressed easily. Let us consider a small surface A centered around a point within the fluid which is at rest. The fluid exerts a normal force on the surface. As the area of the surface becomes small, it is observed that the normal force per unit area tends to become a fixed value. This is how fluid pressure is defined. Pressure is continuous in space and time and is a point property. Fluid viscosity is the measure of resistance offered by the fluid. Imagine the fluid between two parallel plates separated by a distance delta y. The shear stress applied on the fluid is proportional to the velocity gradient of the fluid. This proportionality is true at every point in the fluid, and its constant is called the dynamic viscosity of the fluid. This well-known relationship is known as the Newton's law of viscosity. For most fluids, viscosity is a constant, and such fluids are called Newtonian fluids. Viscosity of a fluid can also be a function of temperature and chemical composition. There are, however, other fluids for which viscosity is a variable and is dependent on the velocity of the fluid. These fluids are described as non-Newtonian fluids. To understand viscosity better, let us perform a quick demonstration. We have 4 tubes with 4 different liquids arranged in the increasing order of their viscosity. Solid metal spheres of equal sizes are dropped into these liquids from the same height. The spheres are sinking in the fluid due to the influence of gravity. It is observed that the sphere falling through the leftmost tube travels faster compared to the rightmost. This is because fluid with larger viscosity imposes a larger resistance to the motion of the sphere. This resistance force is commonly known as viscous drag. Surface tension is another important property which acts at the interface of the two immiscible liquids. It is the tangential force at the fluid-fluid interface which eventually leads to a pressure difference across it. When a thin, narrow capillary tube is inserted into a pool of liquid water, the surface tension force acting at the liquid-air interface causes the liquid to rise along the tube. This phenomena is known as capillary action. Depending on the wetting property of the tube and liquid, we can have either concave or convex meniscus. For example, concave meniscus lead to capillary rise, while convex meniscus causes capillary depression. Temperature of a body is its measure of hotness or coldness. This is very much applicable in the case of fluids as well. It provides a sense of internal energy stored within the fluid. The energy can be exchanged between two bodies. This heat transfer will continue until they reach an equilibrium temperature, after which the energy exchange stops. The temperature is therefore governed by the zeroth law of thermodynamics, which states two bodies A and B, which are in thermal equilibrium with the third body C, are in thermal equilibrium with each other. These bodies are said to be in thermal equilibrium only if their temperatures are equal. The temperature of a fluid can be a function of both space and time. Moreover, it can also change with fluid density and pressure. The relationship between density, pressure, and temperature is given by a thermodynamic equation of state. To describe the state of a substance, it is required to specify 2 out of 3 properties, which are pressure, temperature, and density. With 2 known parameters, the third can be calculated using an equation of state. A thermodynamic phase diagram of the fluid plots these 3 variables in a single plot. In addition to this, it can also be used to describe the phase of the substance. Depending on the pressure, density, and temperature, a substance can be a solid, liquid, or gas. In addition to these properties, there are other thermodynamic properties that become important when dealing with compressibility and heat transfer. Specific heat of a fluid is responsible for the change in fluid temperature as the energy stored by the fluid increases or decreases. The speed of sound is the speed at which Pressure waves propagate in a fluid. It is the function of a fluid as well as its temperature. Thermal conductivity of a fluid is an important property responsible for conduction of heat through the fluid. It is defined as the ratio of heat transfer per unit area through a substance to the local temperature gradient. In nearly all engineering applications, the decision to use a certain fluid is based on these fluid properties. Fluid properties is one of the many important reasons for differences in flow behavior exhibited by various fluids under similar conditions. Now that we have learned what a fluid is, let us try and understand how fluids can be classified in the next lesson.